Okay, any questions? Okay, so we start with S5. We want to get its irreducible representations, and let's work out what the character table is. So for this, we start by considering the representatives of conjugacy classes, and in Sn these are given always by cycle types, so I'll just choose representatives of those. Okay, so these cycle types are indexed by partitions of the number 5. I think I mentioned this before. A convenient way to write these things is in terms of these diagrams called Ferrer's or Young diagrams. I'll just use this notation to illustrate. So that means this means that there are 5 times the number 1. So it's 1 plus 1 plus 1 5 times. This is 2 plus 1 plus 1, and you can see how this is indexing the cycles. This two cycles, two cycles, and one cycle. So when you write cycle types, you typically don't write the single. You don't write 1 bracket 2 bracket 3 bracket 4 bracket 5. But in here we indicating that there are 5 blocks of 1. So this would be okay. So is it clear what this notation is?
Just
so yeah.
The last one, should it be like 1, 2, 3, and 4, 5?
It's the same. Doesn't matter. It's a representative of the class. But I guess if you want to be consistent with that notation, you could do that. I mean, make sure calculations we do that I have in my notes don't get messed up, but it doesn't matter. It's up to conjugation, so these are just elements of that. So the one thing okay, so there's 7. So 7 partitions of 5, 7 conjugacy classes. So we should have 7 irreducible representations. We already proved that. And so tell me some of those representations. We should be able to write down a few.
Trivial one.
So we have the trivial one, which I denote by 1, as we did before. What else? Sign representation, which would be 1. Tell me what this is. What is that? Negative 1. Negative 1. 1. 1. Yeah. What else?
And standard.
We have standard representation, which has what character? So it's a four-dimensional representation.
2, I think.
How do we compute
The
this?
fixed points are 3, so we subtract 1.
Yeah, so this V plus a copy of the identity is just the natural action of S5 on 5 things. So this fixes 3 of those things. So subtract 1 is 2. So it's the number of fixed points of each element minus 1. So this should be 1, 0, minus 1, 0, minus 1. Yeah. What else do we have?
Tensor product of UV.
So if we tensor V with the sign representation, we get another. Tensoring with a one-dimensional representation always will take an irreducible to an irreducible. That's something I mentioned and it's easy to check. So we just multiply these second and third rows. Yeah. What else?
Well, can you use the formula? The number of classes equals the square of the dimensions.
Yeah, but we don't have enough to say much. I mean, we have 4 and 4 is square 16. 16 is 32. Plus 1 is 34. And the group is 120. And we're missing 3 representations, right? So I suggest we first find another representation, at least one more, and then we do this to check what we might be missing. So what other representations?
Can we tensor again with U dash?
If you tensor again, you just go back, right? Tensoring U prime tensor U prime is equal to...
No, I mean
V
tensoring
prime.
U prime with V prime.
Sorry?
Tensoring U prime with V prime.
Yeah, you will get that V. Because the operation of tensoring with U prime is order 2. U prime tensor U prime is U. Yeah, you can see that if you multiply the second and fourth row, you get the chameleon operation. So I mentioned in passing that there was something about the standard representation. The wedge product powers of the standard representation are always irreducible as well. We haven't proved it, but I mentioned it. So we can look at the wedge 2 of V, which will be dimension what? If V is a dimension 4, wedge 2 is dimension
3.
Dimension 5, so 10.
How do you how did we did that? This is on Friday.
What is dimension?
Well, think.
N minus 1 choose N
N minus
minus
1 over 2.
Yeah, n choose 2. It's the basis vectors you can pick out of subsets of size 2 out of 4, so that's 6. Yeah? What's the rest of the character? How do we compute the rest? So the character of wedge 2 of v in any representation is v squared minus chi of v of g squared. Yeah? So we can compute that. So for the identity, well, let's just check. I mean, the identity, this is 1. Sorry, this is 4 times 4 is 16 minus 4 again. It's 12 divided by 2 is 6. How about the rest? What's the value for the transposition? So the value of the character is -2, square is 4, and now we have to subtract the value at the this chi-square is identity, so we get 4 minus 4 is 0. How about a 3 cycle? Well, the value of this is 1, square is 1. It's to subtract the value of the character at the square of this class, but this is a 3 cycle, so square is also a 3 cycle. So it's again 0. This has value 0, and the square of this is what? Is here. So we do 0 squared minus 0, it's again 0. For the 5 cycle, again, the square of a 5 cycle is a 5 cycle. So we get 0 again. For this guy, we get 0, but the square of this is the identity. So we get minus 2. And this, what's the square of this?
3 cycle.
It's a 3 cycle. This 2 cycle becomes identity. I mean, these commute, so the square of this is identity. This is a 3 cycle. So this squares to that. So we get 1 square minus 0.
Minus 1.
Sorry, minus 1. So we get 0. So this, and I seem to have this one is not. Why is this one? This one is wrong. Because I have minus 1 squared, but I have to subtract minus 1, so it's, I have plus 1, so divided by 1. So this one. Yeah? So we can check that this is irreducible by hand, because we can take the inner product of this character with itself, and it should come out to be 1. So to compute inner products with one thing that we need to do, which is compute the size of these conjugacy classes. So let's just spend a minute doing that in general. We did it for S4, although with some back and forth. So the question is, what is the size of the conjugacy class of cycle type lambda in Sn. Lambda here is a partition of the number n. So partitions are something that appear in many different contexts, so it's something good to know a little bit about them. And there are several ways to give a partition. Here, by a partition I mean non-negative integers whose sum is n, and because the order doesn't matter, you can organize them from biggest to smallest. And at some point, these terms are going to be 0, so we can imagine this being continuing up to infinity with as many non-zeros as you like. There's another way to write this, which is possibly slightly confusing. These are not powers, but just a way to write to encode the information. So this means that there are M1 1s, M2 2s, M3 3s, and so on. Okay, so the MIs are called the multiplicities. So multiplicity of the part I. These guys are called the parts of the partition. And these are non-negative integers. And some things are easy to state in this notation, some are easy to state in that. Okay, so what I like to do is, if I give you a partition, I like to compute what is the size of the conjugate class. So, for example, how many elements in S5 have cycle type, a 3 cycle times a suit cycle? I'd like to do that for all the cases.
Just one question. How do you know the number of representatives for the conjugacy class?
That's what I'm trying to compute.
Okay.
This is exactly what I'm trying to compute. What is the size of the conjugacy class? So how many of these there are? You mean how many elements are in this table?
I mean,
Or-
no, I mean how the number of the number of distinct classes.
Well, there is no easy formula. It is the number of partitions of the number n. And there is, in fact, a formula which is analytic, but is somewhat complicated. But it's not something easy to write down. And it grows very, very fast. So there's a very, very large number of partitions for a large number n.
Is there any name for that?
Yeah, it's the number of partitions of n. It's called Pn. You can, so for 1 there's 1, for 2 there's 2, for 3 there's 3, for 4 there's 5, 7. You can put these numbers in Google or in Sloan Encyclopedia sequences and you'll find more about it. I mean, there are the generating series of partitions is something you can write down, so maybe I should mention that. So if you look at the product of 1 minus t to the n to the minus 1, this is the sum of Pn t to the n. Well, this is to declare P0 to be 1. So if you put this in a computer and you take this product up to the number you like to find, then it will give you a way to compute it reasonably quickly, but it's not doesn't quite give you a formula. Yeah. I mean, there's a lot of things about this function, and Pn, you can give a reasonably good approximation of how fast it grows, and so that's something of Hardy and Ramanujan. Ramanujan was fascinated by this function, so there's a lot of work that he's done. It's something like e to the some constant as root n, if I remember correctly. I'll look it up for next time. Okay, so but the question, so I misunderstood your question. You were asking how many columns there are, or columns or rows. That's this number Pn. But now what I'm interested in is giving a column how many conjugacy classes, elements in the conjugacy class there are. Okay, and so the quickest way to do this is to say that the conjugacy, so let me call C lambda the conjugacy class. So these are the elements in Sn of cycle type lambda. Just for now, so the size of C lambda, we can compute it as so if you take some element in the conjugacy class, like the ones we chose, and you look at all the elements that commute with it, the centralizer of that element, then that is the stabilizer under conjugation of the element, and the orbit has size the index of the stabilizer. That's a general fact about actions of a group on a set. So we can, this switches gears, and instead of looking at trying to identify count all the elements in the conjugacy class, we instead look for the stabilizer. And so sigma is an element of this class. It will have a certain number of one cycles, namely exactly m1, with the multiplicity of 1, and a certain number of two cycles, and so on. And if tau is an element of Sn, tau of a cycle, let's say I1 up to Im, tau inverse, is equal to, let me see if I get this in the right order. So this, in this notation, I1 goes to I2, which goes to I3, and so on until the last one, In, goes back to I1. So the conjugate of it will also be an M cycle, and it will be an M cycle that has these same numbers. We'll have these numbers, but now changed by tau. And the question is, if I put this in the right order, it should be tau. Let's only write it down and correct it if I get it wrong. So tau of I1 up to tau of Im. So in other words, conjugation acts on an M cycle by changing the elements of the M cycle and keeping the same order. So 1, 2, tau 1 I1, tau I2, and so. So let's see, if I look at what, I think I got it right. So if we look at what happens to tau of I1 acting on the right, I first hit it with tau inverse, which takes it to I1, and then I1, this cycle takes it to I2, and so at this point, if I input I1, I have if I input tau I1 into this, the first thing is I apply tau inverse, I get I1 in here. This thing takes me to I2, and then apply tau again, so tau I1 indeed goes to tau of I2, and so on. So so if we have a product of M cycles, these M cycles are commute and are sort of independent of each other. These are disjoint cycles. So how are we going to get, what are the possible taus that will take me a product of cycles to itself? So let's do an example, maybe. So for example, this cycle 1, 2, 3, 4, and I'll now write the 5, just to emphasize that this is what we have. So if I apply tau inverse to this, I'm going to get tau of 1, tau of 2, tau of 3, tau of 4, and tau of 5. So what should tau be if I want this to equal 1, 2, 3, 4, 5? What are the possibilities for tau?
It kind of changes the 1, 2 with the 3, 4.
Yeah. The first thing is tau of 5 has to be 5, because there's only one cycle. So the first thing to notice is tau of 5 has to be 5. But now tau of 1 and tau of 2, these two numbers could either be 1, 2, but not necessarily in the same order. They could also be tau 2 and 1. And these two numbers have to be, so these two numbers are either 1, 2 or 2, 1 or 3, 4 and 4, 3. And then the other ones correspondingly. So the option is the two cycles are either swapped, and within each cycle I can move the numbers around cyclically. So in this case it's a 2 cycle, so there's not much, any permutation will preserve the ordering. But if I have a 3 cycle, or say even a 5 cycle, the tau will have to take, if tau 1 goes to 3, then tau 2 has to go to 4 and so on. So what happens then is that the centralizer in general in Sn of sigma is in fact the semidirect product for every I bigger or equal to 1. I look at the cycles of length I, and I get, I can permute, there are mi cycles of length I, so I can move them around. I can permute them in any way. But also within each cycle, I can have a permutation, a cyclic permutation, of which there's I to the mi. So in fact, the stabilizer is a product of what's called a wreath product of a cyclic group of order 5 with S mi. So the conclusion is that this is the order of the stabilizer, and from here we deduce the order of the conjugacy class. So the size of the conjugacy class of type lambda is equal to this number that usually is the number z lambda, which is so it's n. Sorry, this number is n over z lambda, and this number here is denoted by z lambda. So that is to say, this is n factorial divided by the product So we don't need it, but this argument, if you write it carefully, you'll see that this is isomorphic to the direct product of what's called the wreath product of S and I with Ci. It's written this funny way. Okay, so now let's go back to the case of 5 and work out what the size of the conjugacy classes are using this calculation. So the identity is always by itself. So how many 2 cycles do we have? We don't need the big formula for that, but we can check that we got it right. So how many 2 cycles? A 2 cycle is just to give 2 elements, 2 out of 5. So it's 5 choose 2. No, just 5 choose 2, so that's 10. Yeah? If you have to give a 2 cycle, you just have to give which 2 elements are in there, and then you can order them in any way you like. So it's exactly the same as the number of elements, subsets of size 2. How about 3 cycles? You can, to give a 3 cycle, you have to give 3 numbers. Yeah?
20, because we have at most the number of the triples are 60, but every 3 pairs are identified because of the cycle.
Yes. So there is 20. How about 4 cycles? It's the same as picking subsets of size 4,
40?
which is the same as picking size, the complement is 1, so there should be 5 sets of order size 4. But how many 4 cycles can we make out of each set?
50.
So we can pick the first one arbitrarily, the second one is 3 possibilities. Huh?
We can use the same thing because now at most we have 120 not triples but like 4 coordinates, and every 4 of them are identified. So we have 120 over 4, 30.
So I think I'll leave this to you. Let's just quickly go over. This calculation maybe becomes a little bit more useful in here. How about 5 cycles? So 5 cycles, you have to use all 5 numbers, so there's no choice. You could pick the first one to be anything you like, and then the next one you have 4 choices, then you have 3 choices, then you have 2 choices, so it's 24. Okay, so let's use this calculation that we did here for this case. Here we have, so we would have 5 n factorial is 120. The centralizer of this element, there's only multiplicity 1 and multiplicity 2, so we have, let me write it out, 1 factorial 1 to the 1 times 2 factorial times 2 to the 2, because there's two cycles. So that would give 4 times 2 is 16, 120 over 16. It should be 15, is that right? And this one come out to be 20. Anyway, you should check this calculations. Maybe convince yourself that this is the correct statement. And this will give you a way to compute more systematically how many elements are in each conjugacy class of Sn. Okay, so let's just quickly check that this wedge 2 of V is irreducible. we can compute the inner product of the character with itself. I mean, this is a true statement in general, but let's just check it here. So there's a lot of zeros, so that makes the calculation easier. So we have 6 squared. So I'll write it 120, 1 times 6 squared. Then I won't write the zeros. We have 24 times 1 squared plus 15 times -2 squared. And this should be 36 plus 24 is 60. 15 times 4 is 60. And 60 plus 60 is 120, so this is indeed 1. I mean, we know it has to be a multiple of 120, so if it's not very big, it has to be multiple of 1. So this is indeed irreducible. What else? So we're missing 2 representations. What other representations can we spot? How about if I take wedge 3 of V? So wedge V is a dimension 4, so we have wedge 0 of V, V, which could be wedge 1, wedge 2, wedge 3 of V, and wedge 4. And I think we argued on Friday that wedge 4 is the sign representation. This is the determinant of the permutation matrices. So this one doesn't give us anything new. This one we have, this one we have, this one we have. So how about wedge 3? Well, sorry?
Dimension 4.
This is also dimension 4, and in fact is the tensor product with the sign representation. And if we tensor this with the sign representation, what happens? Nothing. The tensor product of this representation with the sign is itself. Because you can see that every time there's a negative sign, the corresponding value is 0, so multiplying by -1 doesn't do anything. So this is actually isomorphic to wedge 2 in this case. So we don't get a new representation. So now we can do what Carlo was saying. We have 5 representations out of 7, so we can see if we can determine what is their dimension. So how are we doing with respect to sizes? The size of the group, which is 120, is equal to the sum of the squares of the reducible representations. So let's call it, we have 2 representations that are missing. I'm going to call it W, and the other one would be W prime, the conjugate, the tensor with the sign representation. Okay, so we're missing, there's 2 numbers, W and W prime, the dimensions of these missing representations that should satisfy, there are no negative integers, and they should satisfy this equality. So what could W and W prime be? See, before, if we had done it before, we would be missing the 6, and then the possibilities would be too big, and maybe not that useful. But now there's not that many possibilities. W squared plus W prime squared is equal to 50, if I'm not wrong. Yeah? So what are the possibilities for W and W prime?
5.
7 to 1.
1 and 7 could also be. So this could be, the only options is that this is 1 squared plus 7 squared, or 5 squared plus 5 squared. So which one is it? Can it be 1 and 7? No, for at least 2 reasons. One reason is that a 1 would mean another one-dimensional representation of this group, which it hasn't, because the group, the commutator subgroup of S5 is A5. It only has 2 abelian one-dimensional representations. Yeah. And why can it not be 7? Because I mentioned before, the dimension of an irreducible representation divides the order of the group. We didn't prove it, but I mentioned it. So 7 doesn't divide 1/20. So this cannot happen, and so we must have 2 representations to dimension 5. So how do we find them? We could try. I mean, we're missing 2 rows. We are in a 7-dimensional space, and we have a 5-dimensional subspace, and we're looking for 2 vectors that are orthogonal to it. So we can set of equations. That might actually be possible. I haven't tried it, but I'm going to do something slightly different. What else can we try? I mean, of course, you shouldn't think that this is what you would do every time you face a group. You'll, start thinking about what you should do. There are some systematic things you can do, but this is just, sadly, you're not going to do this for Sn in general. You want to have a more systematic way of doing it for all n. So wedges of V are not going to be very useful. What other ways do we know how to construct representations? We could take sim2. Yeah? So let's look at sim2 of V. This is of what dimension? Actually, let me put it down here. It's not going to be reducible, but I want to list the character values in order.
The dimension would be
10. So it's, we call that the formula is n plus k minus 1 k. So this is 4 plus 2. Well, I mean, k is 2, so it's easier to say. This is n plus 1 over 10. So it's 4 plus 5 times 5, 20 over 2 is 10. So this is dimension 10. So it's certainly not going to be reducible, yeah, but it will break up into pieces. And the pieces that could break up are the ones that we have so far. So if we're lucky, maybe we'll have a piece that has dimension 5. And this is what indeed happens. So let's compute the character of sim2 and decompose it according to the characters that we have. So how do we compute the character of sim2? The same way we did before, but instead of minus, plus. Yeah. So let's just check. 6 squared plus 6
minus 6 plus 6, 12,
6
6,
or
again
4,
6.
Sorry, why 6? 4. 4 squared plus 6. 4 squared plus 4 over 10. Okay. So how about the next guy? This was
Identity, so
2 squared is 4 plus 4 divided by 2, so that's 4. Yeah. This guy, 1 squared plus 1 is 1. This one is 0 plus 0 is 0. Here, minus 1 plus 1. No, minus 1 is 0.
It's square.
Huh?
This is 2.
This guy square is the identity, so we get 4 plus 4 divided by 2 is 2. This guy square is a 3 cycle, so we get minus 1 squared plus 1 is equal to 1. Okay, so can we see what are the multiplicities? So if I take the inner product of this character with the trivial representation, I'll see how many times the trivial representation appears in its decomposition. So let's see. We have to do 10 times 1. Write it out. So this is 120 divided by 1 times 10 times 1. And then 10 times 4 times 1. 20 times 1 times 1 plus 2, sorry, plus 15 times 2 times 1
I think 13.
plus 20 times 1 times 1. Huh?
No.
Is that correct? And if you compute this, you get that this is 1. Okay? You do the same with the sign representation, you're going to get 0. And if you do it with the standard representation, you get 1. So it's just this arithmetic calculation. So that means that this representation has a copy of the trivial representation, a copy of this standard representation, and then the difference, what's missing is something of dimension 5. We claim that that is one of our representations, W. So sim2 of V is U direct sum V, direct sum W. So we can compute the character by subtracting from this last row, the row of V and the row of U. So let's see, we have 10 minus 5 is 5, 10 minus, 4 minus 3 is 1, 1 minus 2 is -1, 0 minus 1 is -1, 0 minus 0 is 0, 2 minus 1 is 1, 1 minus 0 is 1. So I hope I did this right. 1 minus 1 is 1, 0, 1. That looks right. So again, this, I could have been wrong, and this again has a trivial, is a decomposition of this W is, it could be U 5 times or something, but it's not. You can check that this is actually reducible. And what's W prime, as already suggested, is W tensor U prime. So if we multiply by the sign representation, we see the missing one. Okay, so we have done. We have computed the character table of S5 by brute force calculation. As I said, we're not going to then do 6 and then 7 and then 8. I mean, at some point.
How do we guarantee that there aren't any other reducibles?
Excuse me?
Maybe there are other reducibles?
No. Why are there no other irreducibles?
Because they are the same as the number of classes.
Because there have to be as many rows as columns.
Yeah.
So no, we're done. And if you look at this calculation we had over here, the formula doesn't have any more room for the sum of the squares. It's already 120. Okay. Now, maybe something to point out is that so far, all the cases of groups that we've done, well, haven't done that many, apart from the abelian groups, we did S3, S4, and S5, they all have character tables that have integer values. And this is, in a way, misleading because it is not the case for arbitrary groups. In general, arbitrary groups will require characters that have values in other cyclotomic extensions of Q. Okay. In fact, I think I won't do it now, but we will compute the character table of A5, and we'll see that we have to introduce square root of 5 as a possible character. The character values will involve square root of 5. So yeah, maybe I should do that now. So the character table of A5. So A5 is a normal subgroup of S5, or it's a simple group of order 60. And if you look at its conjugacy classes, it would correspond to conjugacy classes, the cycle types of even permutations. But here comes a phenomenon that is quite common. The even conjugacy classes are the ones that have a 1 in this row. So a 5 cycle is an even permutation, but what happens is that every 5 cycle is conjugate to all other 5 cycles, but there are 5 cycles that you cannot get from one to the other by means of an even permutation. So viewed as conjugacy classes of A5, 5 cycles divide into 2 conjugacy classes. So these 2 5 cycles, again, are conjugate, but only conjugate by an odd permutation. So they become the same class in S5 if you extend from A5 to S5, but they're not the same in A5. So these are the conjugate classes of A5. And so what happens is that everything else stays the same, the numbers are the same. We have 1, 20, 15 here, but this 24 for the cycles becomes 12 and 12. And similarly, if you take a representation of S5, you can restrict it and forget what S5 does and only concentrate on A5. So you can restrict representations to subgroups, and you will get that if they were irreducible, well, they may stay irreducible or may not. Okay, and so I'll just quickly go over this. What happens is that we can look at this trivial representation, certainly we always have. Now the sign representation we don't write down, because when you restrict to A5, it becomes the trivial representation, because everybody has sign +1. So it doesn't give us anything new. The standard representation, however, we can restrict it to A5 and remains irreducible. We can check this by computing the inner product, for example, with itself. W and W prime remain irreducible, but when restricted to A5, they are the same. The same with V and V prime. They restrict to irreducible, but in fact to the same one. And now we see a similar phenomenon to the conjugacy classes. The 6-dimensional representation actually breaks up into 2 irreducibles of dimension 3. So we have an X and a Y of dimension 3 that when added together gives us the restriction of wedge 2 of V to A5. So the restriction of A2 of wedge 2 of V to A5 becomes isomorphic to X direct sum Y, to irreducible representations of dimension 3. Okay? So if we want to know the character table, what are the characters, we can do some linear algebra and find what the character values are. And so let me just tell you what it is. I'll leave it to you to verify this. So this -2 that we have here becomes the sum of -1 and -1. And these two things become epsilon and epsilon prime, where epsilon is the golden ratio, 1 to root 5 over 2, or anyway related to the golden ratio. 1 minus root 5 over 2. So we see an example now of a non-abelian group where the character values of some of the representations are not necessarily rational numbers. They always have to be algebraic integers, as we discussed, and in fact they are in some cyclotomic extension. In this case, these numbers live in the field where you join the fifth roots of unity. And an interesting thing that we'll come back to is that, for example, here the S5 doesn't have a representation, irreducible representation of dimension 3. Yeah? So if you think of the group S5, it cannot act in an irreducible way in 3 space. It just doesn't it cannot be done. If it acts on 3 space, it will have to be a direct sum of trivials or sign. Whereas A5, what this is telling us is that in fact it acts in 3 space. And since if we look at the row, there's no value that has a character of value 3 except for the identity. So this means in fact that no element of A5 maps to the identity. So what this says is that the group A5 is sitting as a group of linear maps in 3 space as a subgroup. There is the implicit map from A5 to GL3 is injective. And so in fact what we'll see is that A5 is the group of rotations of the icosahedron. Okay, so this that we're seeing here has a geometric counterpart. In fact, in 3 space, there's only very few groups, finite groups that act irreducibly, and these have to do with the Platonic solids. Okay, so we'll see that in the remaining classes. But now, so in going in that direction, what I like to now do is discuss somewhat of a more subtle point, is that we have been working with complex numbers. So this statement that you see here tells us that A5 is a subgroup of GL3 of the complex numbers. And we may ask, is it the case that we can see this group A5, or maybe some other group, as a subgroup not just of GLN of C, but GLN of R? And that becomes a somewhat delicate question. I want to talk a little bit about that. So when is it that representations actually are defined over R? So by that I mean that we have a group G and we have a homomorphism from G to GL of V0, and V0 is a vector space of finite dimension over the real numbers. Now, if we have a vector space V0 over the real numbers, we can extend scalars to C, and that gives us a vector space over C. So this representation, you can view it, this sits inside GL of V. So any representation that of this kind that goes to a real vector space is just a complex one after extending scalars. So it's of the kind that we study. So we call this such a row on GLV that comes from an intermediate real vector space action. We say rho is a real representation. Now, if the representation is real, then that means that rho maps to, if you pick a basis of V0, maps to matrices that have real entries, and therefore its character, which is the trace, has real values. Yeah? So for example here, these two representations, these epsilons are not rational, but they're real numbers. And what's a little bit complicates things a little bit is that the converse of this is not true. So if a character has real values like these two here, a priori we don't know if they actually can be realized as matrices that have real entries. So what we want to discuss now is how do we tell if a representation, given its character, how could we tell if it comes from a real representation or not? And this is useful. This is a question. It's not just an idle formal question. It is useful because, for example, again, we may want to know, does this tells us that the group A5 is a subgroup of GL of GL3 of R, or doesn't it? So if it's a subgroup of GL3 of R, it means that it will have to, it acts on 3 space and on our actual space we live in, and therefore it will have a geometrical meaning, direct geometrical meaning. Okay, so to give you an example of something that fails, so that it illustrates why this converse is not true, and it will also be a useful thing to think about this question, is to do the following. We're going to look at the group SU2, which is the group of, concretely we can give it as a group of matrices that preserve a positive definite Hermitian product in C2. Now, by taking choices, you can be specific and say this is matrices in SL or GL2 of C, so 2 by 2 complex matrices, invertible complex matrices that satisfy the G transpose inverse is equal to G conjugate. So, well, what we can think is that this is G transpose conjugate times 1, 0, 1. Okay, so these are unitary matrices, and actually the S stands for determinant being 1, so it also say determinant is 1. So U stands for unitary, S for special, which always means that you impose the condition that the determinant is 1. So this is a simple way to think of it, but it kind of comes from this statement that this G preserves this Hermitian product, which we take it to be the standard product, standard unit product in C2. Okay? So concretely, if G is a matrix with entries A, B, C, D, then since we want this condition to hold, and we want the determinant to be 1, so AD minus BC is 1, G inverse is DA minus C minus B, and so the transpose, we want the transpose of the inverse to be the conjugate, so transpose inverse is DA minus B minus C. We want this to be equal to the conjugate, so A bar, B bar, C bar, B bar, and it follows that G is of the form A, B minus B bar, A bar. And because of the determinant we are asking it to be 1, they have to satisfy these conditions. So these are the matrices that we are interested in. So you can see this is in fact a subgroup of GL2. The product preserves the same Hermitian form. So this is a subgroup of GL2C. And the thing to notice is that the trace of G is equal to A plus A bar is real. Now, suppose G in SU2 is a finite group. Then what we would get is a representation of G. So G maps into S of SU2, which is sitting inside GL2 of C. And so the character of rho is real because the matrices of that rho that represent rho, represent how G acts via rho, are in SU2, which has every matrix as real light. Now, so what this tells us is that we have, i.e. we have a two-dimensional representation of G with a real character, or real value character, be careful. Okay? And I claim that that restricts what G can be significantly. Because this is let me make this statement in general. In general, if rho maps from G to GL n of R, so it's a real representation, it fixes a positive definite inner product over R. So what we say now, we have imagine you have a representation that is happening with everything is happening over R. The matrices that represent the elements of G have real entries. I claim that it preserves a usual real bilinear inner product, which is positive definite. No mention of complex numbers in here. Okay, and the reason, so the proof of this is the same as before. In other words, you start with any old inner product that you like on your vector space over R, and then you average. Start with this and average. The sum of the translates of this inner product will be also positive definite, and the total average will be fixed by the group. So you get a positive definite inner product on your space, everything defined over R. The matrices that you're using for G have real entries, everything is over R. There's no C anywhere. So if you have a real representation, you necessarily will fix a usual real inner product. Okay. Now, if you are in 2 dimensions, so G, by this statement, G fixes an inner product. Okay, so let me just say, if rho is real, then G fixes an inner product on R2. Okay, but the inner products on R2, they're all isomorphic, positive definite inner product. So that means that G, you can map it into the isometries of R2. But in fact, it has dimension, it has determinant 1, so G actually maps, well, here maybe not injective, it doesn't matter. G will fixes the standard inner product after changing basis, and so G maps to rotations of R2, because the determinant is 1. But the rotations of R2 of determinant 1 is SO2, this is the name of rotations in general, or O stands for orthogonal, S for, again, special, which means determinant 1. And what group is this? What are the rotations in the plane?
Cosine?
It's just a circle. Okay? So this is abelian. Okay? So a group we started by assuming G was a finite group of SU2. We deduced that G actually has to be a subgroup of SU2, SO2. Well, I guess I could say that this is injected, nothing else will change. So G is a subgroup of an abelian group, then it has to be abelian. So the conclusion is that if we have a finite subgroup of SU2 that is not abelian, then it cannot have this representation that arises from this inclusion into SU2 is not real. So i.e. if G is a subgroup of SU2 which is non-abelian, then the representation that comes from viewing it as a subgroup of SU2, which is a particular subgroup of G on through C, is not a real representation, but has real character. It has a real valued character. So you could say, okay, well, fine, but then how do I know that there are non-abelian subgroups of SU2? Otherwise, if this will example be vacuous. So do you know a non-abelian finite subgroup of SU2? Let me show you an example. There's a few. These are very interesting groups. So to do this, let me introduce one more thing, which are the Hamilton quaternions. So this is a algebra, so usually denoted by this H. This is an algebra over R of dimension 4. So it's a vector space over R is dimension 4. It is generated by basis vectors, 4 basis vectors that are traditionally called I, J, and K. This notation goes back to Hamilton and it's pretty much written in stone. Everybody uses this. And the key thing about these basis vectors is that this is a non-commutative algebra, and the key thing is that ij times j is equal to minus ji, and I times j is k. And from there, is an associative algebra with associativity and these rules, then you know how to multiply any elements of the algebra. So one way to describe this slightly different way, which I'll use and it'll be convenient for what we're doing, is to think that what you have is C, which is this first piece with 1 and I. Think of I as the same I as in the complex numbers. And then a second copy that gets multiplied by a new quantity called J. I guess I should also say I squared is equal to J squared is equal to minus 1. So one way to think of H is that you add to C one new quantity J, whose square is minus 1, but then it doesn't commute with j. So if you have a complex number, you can swap a and j in the product, but in the process of swapping, the complex number a gets conjugated. This is the reflection of that statement about I over there. Okay, so if you multiply two pairs, a plus bj times c plus dj, you will just use this distributive law, and you'll hope, and the rules that we have about moving j around, and you'll see that this is again of this form with this formula, and exactly this matches multiplication of the matrices A, B, C minus B conjugate A conjugate, and C, D minus D conjugate C conjugate exactly matches that. So what this is telling us is that the quaternions, which is this four-dimensional real non-commutative algebra, maps to the matrices not GL2, but so the matrices, so C2 times 2 this is a homomorphism of rings, of algebras, and in here we have the quaternions of the form A, B, J. So this, maybe we write it. This map takes A, B, J to the matrix A bar, B. A, B minus B bar, A bar. This is an algebra homomorphism, and somebody here which satisfies that A bar plus B bar is 1 gets mapped to somebody in SU2. So if I look at H1, defined to be the pairs A, B, J, such that A plus A bar, B plus B bar is 1, then H1 under this map gets mapped to SU2. And so this actually is an isomorphism. So it's a different way to give the same group. You can say that SU2 is the invertible elements of the quaternions that have norm 1, the norm being this quantity A plus A bar times A bar plus B bar. I should have said this before, this algebra is a division algebra. So every element in this algebra is invertible except for 0. And as you may know, it's a theorem, I guess, Milner completed the proof that if the only division algebras over R are the reals, the complex numbers, the quaternions, and then if you relax even associativity, there's yet another crazy algebra called the octonions. And that's it. There's no other way to create a multiplication over the real numbers such that the resulting algebra is a division algebra. So this algebra plays a central role because of that. Anyway, our group, now we change gears, and instead of talking about SU2 as matrices, we can think of it as unit quaternions. And so now is not too hard to give an example, because we could just look at the quaternion group. So we look at the 8 elements given by these. Yeah, and so now you've probably seen this group before as an abstract group, but now we can see it as a subgroup of the H1, and this is a group which is non-abelian finite and maps over to a non-abelian finite group of SU2. Okay, and so the character table of this group, so these are the Hamilton, well, this is the quaternion group of order 8. And you easily can work out what the character table is. The conjugacy classes are given by 1 minus 1, I, j, and k, plus or minus I being one class, plus or minus j being another, plus or minus k another one. And you'll find that it has it has 4 one-dimensional representations, and then one two-dimensional representation, which comes from this map here. The only, the I and the J and the K are matrices that have trace 0. If you look at what happens here, for example, I goes to I, the matrix I 0, 0 minus I, which has trace 0, and J goes to a similar thing. Whereas plus or minus 1 map to 2 identity and minus identity, which have respectively trace 2 and trace minus 2. So that gives you these 2 character values. So this is a character of this group that has real values, but is not real. You cannot see this group as acting on a 2-dimensional real space. So as a subgroup of SL2R, or GO2R. Okay? So we will continue then and figure out a way to, out of the character, deduce whether the representation can be given in terms of real matrices, whether it's real or not. So I remind you then, we now have class Wednesday and Friday this week, but we moved them over to the next week. Okay.